Hi, my name is Katie, this is Amy, that's Amelia, and that's Sophie. Our project is the James Webb Space Telescope. The James Webb is due to launch in March 2021 and is the largest space-based telescope so far. The James Webb hopefully will help us to discover more about our universe. We were given an opportunity in school to take part in an event to categorise stellar objects. 2 other schools joined us for the day where we spent time learning how to categorise stars and go through untouched data from the Spitzer telescope. Our aims for this project were to successfully analyse and categorise objects in time for the James Webb launch. Our other aim was to help astronomers find potential and unusual targets for the James Webb. Also, to bid time for the James Webb.
In order to classify stars, we have to go through a process. We used AOR keys, which are like these numbers which correlate to a certain star. And those are used to find our desired star on the Spitzer database. When we access the Spitzer database, it shows us an image of a star and the star's spectra. From the spectra, we can identify the type of star it is, the star's characteristics, and stuff that the star contains. And then we use a decision tree to help us analyze the stars. When we look at a graph of a star, we have to go through this decision tree in order to categorize it. When we first look at the spectra, if the gradient is increasing or decreasing to the right, then we go on to the next question. And if the gradient of the spectrum is rising above 30 microns, then that tells us it's a forming star. So as you can see for the forming star up there, the gradient is increasing to the right and it also goes past 30 microns. However, if it does not increase above 30 microns, then it's a planetary nebula. As you can see, there's a similar pattern. It's increasing to the right. However, it doesn't increase above 30 microns, therefore it can't be a forming star. If there's a dip between 6 and 8 microns in the spectra, or a steep decrease between 5 and 7, then it's an evolved star. As you can see there, there's a steep decrease and it's decreasing to the right. And if that doesn't apply, then it's either an ordinary star or a rarer object, which is one that we actually discovered.
With all the data that we collected from the Spitzer, it means that we get new, different traits to identify with stars. Within the first 100 objects that we looked at, we found an unusual and interesting object. The object was strange because the star's spectrograph was much smoother than usual, so there's no spikes or dips or anything like that in it. And this shows a lack of ionization of the gas around the star. Initially, the star was thought to be a planetary nebula, but after further investigation by Dr. Olivia Jones, it was actually an oxygen-rich evolved star that we'd captured at a rare stage in its life. With the upcoming launch of the Space Telescope, the need for more knowledge about these stars increases, and there's still many new discoveries to be done. And with every new discovery becomes more and more new and more specific classifications.
Our next steps are to obviously continue categorising all these still many unidentified stellar objects. At school, we plan to teach our STEM Academy how to categorise them and just sift through the copious amounts of stars still uncategorised, because more hands never hurt anybody. But increasing the information that we have makes more categories and gives us more knowledge in this pioneering field of science. With this opportunity and this discovery, we've been given many new experience and the chance to meet a plethora of different people. As well as this, the project has opened many doors for us and even maybe a possible career or university study in this field of science. Overall, the James Webb Space Telescope will hopefully shed light on some age-old questions. However, there's still an abundance of research and exploration to be done. However, with new technology and just a spark of curiosity, we can surely discover the secrets of the universe.
Why did you start this project?
It was told to us by our physics teachers that we had the opportunity to work with untouched Spitzer data, and it was also just an excuse to go out with some classes at school, so it turned out pretty well for us, I think.
All the best things start. An excuse to get out of some classes. Good. Excellent.
How many objects did you actually investigate or look at before you found your special one? And was it frustrating to have to go through so much data before finding that nugget, if you like?
We really didn't. We had about 10 to go through before, and then you get some more. That was our third one.
It was really early on. Yeah.
So it was pretty lucky, I'd say. But it looks so strange. We originally thought it was a planetary nebula, but then we were like, wait a minute, that can't be right. So we flagged it up, and obviously Dr. Olivia Jones did some more research, and you all have the opportunity to find something like we did, so you never know.
Back a slide. Go back a slide. So actually, Libby's here. So she's actually gone on to do some further work on these objects. Because of some of the things that have been found out here, and actually similar objects found by some other schools as well, all within the same type of class. So there's this kind of really proper partnership that's going on between all the work that you're doing, and don't forget about the scientists and other people that you work with that has an impact on them as well. Okay, so thank you very much, Larbert. You can go back to your seats.